Okay, so welcome on board, everyone, and thanks very much for showing up for the hydrogen group webinar series. This is the second one or third one, and there will be quite a few more coming up in the long run. And our hope and aspiration is that we keep this series going through to encourage more and more people to engage in hydrogen discussions, both on technical side, the business side, but also the public-facing side of things as well. So we're expecting quite a few people to sign up, to join up, but we had a slight delay. My apologies for that, due to Teams technical issues. We got that addressed and most people have joined in. So I suggest as we get along, please write the questions on the chat and we can go through them later on after presentation is done. All the mics are off for now, but will be opportunity to ask questions through the chat, and also we can unmic later on if we do need to or we have to. So our speaker today is Professor Nadim Faisal, who is a professor at Robert Gordon University, specializing on coatings and surface engineering. And he has a huge expertise on materials, have a huge background of coming through different universities, including Harriet-Watt, probably the most recent, apart from RGU. He's been with us for almost 9 years, which is a great colleague to have as well. So Faisal, welcome. Please go on with the presentation when you're ready.
Thank you, James. Right, so good afternoon or good morning. Where are you from? I'm Nadim Faisal. I'll be talking about my understanding and my interest, which is related to high temperature electrolysis. So my background is coating, thermal spray coating, and understanding the surface micromechanical behavior. So I normally use sensors and apply various type of loading to understand how the surface degrades. However, I've started looking into various applications of those coating, and this is one of my current interest, which is related to electrolysis. Right, so as we all know, hydrogen is right. So before I go there, I would like to summarize who we are. I'm from RGU. Currently, we have got 16,000 students, and from many nationalities. We are based in Scotland, means in Aberdeen, if you see where it is. Is very sunniest placed among the sunniest placed in UK, but the weather changes very frequently, and that's my office. Right. And before I talk about thermal spray and related subject, electrolysis, these are my partners, collaborators, sponsors, and colleagues who I have worked or working since my journey in coating in 2001. I started my journey at ARCI, which is in India, and then moved into Harriet-Watt. And then since my PhD, I have collaborated with various industries and university and lab partners. Right, so in today's presentation, I'll be talking briefly about hydrogen, and then using high temperature, looking into materials and structures. What are those elements or materials, how we process and manufacturing method. I'll share my example of manufacturing using thermal spray coating and the issues and challenge, and touch upon briefly about modeling, characterization, and testing needs, and then a few ongoing projects in this area. So as we all know, globally, hydrogen has attracted interest, I would say, largely in or last 2 years. My interest started more than a year ago. And this is a high-level data which we all know, which is 5 gigawatt of low-carbon hydrogen production in Scotland by 2030. So that's a very ambitious plan. And whoever got interest in it, we need to do things, collaborate or develop or put proposals, develop technologies from various TRL level. Right, hydrogen. So what is hydrogen? It is a colorless, odorless, tasteless, and non-toxic gas. And we all know it disperse like nearly 4 times as fast as natural gas. And it has the highest energy mass of any comparable, which is about 143 megajoule per kg. The content, the higher heating value content, 39.41, and the cost is about £10 per kg in the UK. Well, the cost is likely to decrease over time. And these numbers are important if you want to do certain calculations, especially the higher or lower heating values. I'll show you one calculation later on. So this is some numbers if you're talking about calculation. Now, the other thing which we would like to know is about what is the basic principle, how it happens, what are the voltage requirement, and so on. So Faraday's laws of electrolysis, it was proposed long ago by Michael Faraday. And this is related to chemical change or current at the electrode, electrolyte, electricity, or equivalent weight. So means you need about two electrons. You need to create a molecule of hydrogen. So that is the basic requirement. And we need 1.48 volt to split the water. So that is number again we need to look into. And then we look into how we use electrodes, means anode, cathode, electrolyte, or combination of these, and integrate with feedstock. I'll talk about what feedstock is. And then apply a voltage so that you can split water. Okay, so my presentation today will be largely on materials and manufacturing techniques and issues associated with that. I'm not electrochemist, so I'm not going to that far end of electrochemistry and electrolysis. Right. In terms of how much hydrogen is needed, I just did one calculation, which is considering the miles we travel in the UK in a given year. So this is a historical record taken from the government website since 1949 until 2021. And you'll find that currently we are about, I would say, average 350 in 2020 or 2021. It has gone down a little bit, average about 350 or so billion miles we drive in the UK. Now, there are about 8,000 petrol stations in the UK. And if we have to replace those with hydrogen, then how much we will need as of today. Now, what I did a calculation. If you can see the details of this calculation here, I came up with a number which is about 16 million kilogram of hydrogen will be needed every day if we have to cater the needs of transportation only. So now there are various other application industries, hospitals, and many other application. So you can add all those. There are huge requirement, or will be if you're talking about economy, hydrogen economy. So we need to scale up the production of hydrogen. Now, one of the topic I'm focusing today is hydrogen production at high temperature. Right, there are various sources where we can get high temperature heat. So one is a concentrating solar cell, another one is nuclear, geothermal, and also various waste heat. And then you can use solar, wind, ocean, and nuclear source to produce electricity. And you combine these heat and electricity to do electrolysis. Now, heat is cheaper than electricity, but you need to hold it so that you can use the heat for electrolysis process. So that is a requirement. Now, if you look into the two different sources here, one is the nuclear power plants, where you can have a lot of heat wasted. So the efficiency is about 35%, and about 60% of the heat is wasted in nuclear power plants. So you can see in this left side, there are a number of places where these nuclear power plants exist. So as we speak, a lot of heat is being wasted. How we use it? Can we use it for electrolysis? Then how about photovoltaic? If you look into the energy, so that you can see the distribution. So there's a lot of high temperature which is going into atmosphere, and we are not using it for various reasons. Considering geothermal energy, so currently in UK, there's not much work going on in geothermal. However, in time to come, once the technology has matured up, so that is another source of energy, a high temperature source, which could be considered for electrolysis. Now, looking into the work done by Professor Gluyas at Durham University on the right side of the screen, this is a map how the total heat is wasted across country. And there is a record. I've taken this from 2018, and the total waste heat is about 390 terawatt hour. And most of that is through electricity generation process, most of it, and some industrial process. So that is quite a lot of heat we are wasting, and means if we can enhance how to contain and use it for various purpose, that will be amazing to do. Right. If you go back a little bit to the basic and think about that, you're using water, so up to 100 degrees centigrade here, it is in liquid phase. And then if you increase the temperature up to 1000 degrees centigrade, the energy demand for electrolysis at high temperature, you can see that if you increase the temperature, then the electrical demand will go down. Yes. So anything above 100 up to 850 degrees centigrade, it falls into the category of high temperature system. You can have more higher temperature, but you remember all these electrolyzers or structures, they are made of material. For example, steel is used, so it will start corrosion. It will not resist at high temperature. So there is a limit to what temperature you can operate those electrolyzers at. So this is something to remember, that how you can optimize your electrolyzer design so that you can make good use of it. Now, looking into the technology readiness level of some of the important hydrogen production method, there are a number of those. I don't want to go through each of those, but I've highlighted those two blocks. And they are they have considered all these electrolyzer types, and I'll talk what they are, mainly focusing on high temperature. So, however, there are many other methods which can be used for hydrogen production. The most common one is methane reforming process. And hydrogen economy, there are all sort of all different means to produce hydrogen, but currently the focus is producing through electrolysis mechanism. Right, if we look into the details, different type of electrolyzer, the first one, which is very commonly used across industry, is PEM, proton exchange membrane. The feedstock they use is water and electricity. The another one is anion exchange membrane and alkaline water electrolysis. All of those combine water and electricity, and they are able to split to produce hydrogen. Now, if you increase temperature, so you add heat as well, it becomes solid water electrolysis. You can also supply water in the form of vapor, so steam. So that becomes solid oxide steam electrolysis. Now, if you can have only water and heat, so that can be used at nuclear power plants. So that becomes thermochemical water splitting. And then the last two where you can use sunlight with water, one is photolysis, and the last one is photoelectrochemical method. So I've broken down into these many types based on the type of feedstock, just to simplify it. Now, in all these cases, you need a combination of water, electricity, sunlight, or heat. And then there is a potential to design a new electrolyzer as well. Now, as I said, you need material. So when you have got material with water, things will corrode. So you're talking about high temperature, so there will be an impact of that. So thermal degradation will happen to the materials and structures. Again, you have got the sunlight coming from concentrated source, so that will also degrade the structure. You're talking about electricity, so material breakdown is a problem. Mechanical, so things move, the pressurized conditions, so static and dynamic loading will impact the integrity of the structure. And also there will be wear, means cracks and delamination, because they are made of electrodes, multiple layers, different strain. And then last but not least is electrochemical attack. So all these combination will be there when you're operating high temperature electrolyzers. So what you do, you design your electrolyzer in a way where you can mitigate all these issues to enhance the performance and durability. And also you would like to reduce the cost, because these are expensive material. Okay. Now, looking into high temperature types, the last four types I mentioned earlier, which is solid oxide, steam electrolysis, photolysis, photoelectrochemical, and thermochemical. So my interest currently is high temperature steam. I'll show you why, and also the thermochemical water splitting. I would like to work on all of those, but maybe at some other time. Now, in all these cases, you can see take one example of solid oxide. You have got anode and cathode, and you have got a dense layer, solid oxide, dense layer. And then you supply power, and you can, on one side, you can have hydrogen, other side, you can produce oxygen. So this is a basic schematic of that one. Now, the high temperature is same. For photolysis system, all you need is a catalyst where you can have a photon going onto the surface, and that material should be able to split. So you have got H nu. So that is the photon energy you have to look into. So the photon energy is very important, starting from 1.2 to 0.01. So that is a typical range. You have to look at, normally you use somewhere here. So you have to select the right material for that purpose. And then you have got a photoelectrochemical method, where again you use a photon energy H nu. And then you have got a thermochemical method, where you have got a membrane. On other side, you've got anode. On one side, you've got a molten salt going through, so high temperature, and then you can split the water on the other side. So that is the simple description of all these electrolyzer types. So I'm talking about anode, cathode, electrolyte, dense layer, and so on. So it means you're talking about material, catalyst, electrodes. Looking into the high temperature thermochemical one, So this is a simple schematic diagram how the nuclear power plant looks like. You have got a molten salt reactor. So the fresh fuel comes into, and then there is a system here where you can reprocess the spent fuel. So you've got the huge means molten salt, means the high temperature can go through a heat exchanger system, and then the steam can be taken from that. The steam can go to the steam turbine, and then some steam can go to the electrolyzer you are or like to use. So in this case, you can use a steam electrolysis. And then you can also use a thermochemical electrolysis system at this point where you have got a high temperature or molten salt flowing through the channel. So you can also use the electricity available to put through these electrolyzers. Now, there's a huge amount of heat waste happens currently. And I understand there's no such high temperature electrolyzers currently in use at those nuclear power plants. There may be, I don't know in much detail. Right, we need to think about the structures and materials, because you can see the molten salt is going through the channel. So it goes through structures. So it makes contact with the materials. So if I'm talking about the structure or substrate which has been coated with thermal spray material. So whatever literature we have seen, the test has been done between 500 to 1300 degrees centigrade. So the duration is very broad. So people mostly they test about 20, 30 hours, but somebody have tested at a very long duration, 300 hours. The coating thickness normally is normally in thermal spray, you would have 300 micron. So as low as you can go 100 micron, but few of them have also manufactured coating, which is about 4 millimeter. And I'll show you later that how higher thickness is not a good idea. And also if you're manufacturing coating, so typical powder size are about 45 to 90 micron. And if you do corrosion analysis, the corrosion rate they have reported is between 14 and 31 per year. That's quite high. If you take a mild steel and put in seawater, the average reported value or acceptable corrosion rate for mild steel is about 100 micron per year. So if you compare with that number with this 14 to 31 millimeter per year, that's quite a lot. So if you assume your molten salt is going through a channel and that is made of some steel or superalloy, that will degrade the system. So that's why you need to have a coating which can protect the structure so that you can use that for a long duration. And we also have a huge amount of thermal energy available. So it will be good to have a system where you can store those thermal energy to enhance the efficiency. Now, looking into the corrosive environment, there are quite a lot of corrosive environment at high temperature which has been investigated. So it depends how your reactor is designed, electrolyzer system is designed. You can select, so most common one is copper chloride. But there are research which has been done using these corrosive salt. Now, looking into the materials and structures. Now, as I said, without material, nothing happens. So this is a periodic table, and the temperature is related, means it is melting point of these elements. So what I've done, I've selected various material which has been reported from various published source, and so this is solid oxide, this is photoelectrochemical, photolysis, and thermochemical. You'll find a lot of material examples which has been reported for solid oxide water electrolyzer. Very few on photolysis. Titanium oxide is the gold standard for photolysis, but some of them have tried zinc oxide as well. Thermochemical, YSZ, Ytteria, stabilized zirconia, alumina. These are commonly used material. For photoelectrochemical method, very few work done, mainly metal oxides, tungsten oxide, titanium oxide, iron oxide. So again, these are very recent work. And you can see where those elements sit in the periodic table. So if you're thinking about manufacturing catalyst electrodes at high temperature application, so you can select those elements. And from this list, you will have some idea of what sort of composition you need if you're considering thermal spray method. Now, if you go beyond thermal spray and look into what are alternative manufacturing methods. So here, my student, Vinod, he helped me to compile a list of manufacturing methods which has been used for these 4 electrolyzer types. And in the block, you can see these are the material used and various manufacturing methods. So there are a range of manufacturing methods, range of material types for high temperature. And that was surprising. So this is helpful to us to understand because there's not one material, there are many material in the library, and how we can use it, source it, and develop electrodes which is efficient enough. So many data you're talking about, so many behavior and properties and ways of doing it. So you definitely need beyond conventional method to understand all these information. Now, those are related to the surface or the material you'll use to do the coating. How about the substrate? Because thermochemical, you need a substrate on which you will be doing the coating. Now, I've categorized these material into 3. So these are largely steel, these are superalloys, and then you've got additional other type of material. Based on the availability, as you can select a relevant material, but these are the typical one, what I understand have been used. Now you select any material, these will operate at very high temperature and varying loading conditions. So if I take example of this plate, what happens when you've got a substrate, you do the coating will be formed layer by layer. Based on the strain being built up during coating, things will deform. Either it will go this way, where you have got a huge tensile stress, or you can go this way, where you've got a huge compressive stress. So high extreme of those is not desirable. You would like to have a residual strain inbuilt during manufacturing, which is sustainable under external mechanical load. So this mechanics we have to be aware of how the coating will form. So this is just a simple example of a single layer, because you have got a different substrate, different elastic modulus, different Poisson ratio, different thickness. So whatever you do on top of that, it is likely to change as soon as you do the coating and also apply in various temperature condition. Now, surface and interface is an issue, how you manufacture it. So it is an hypothesis here, a simple schematic diagram where I'm suggesting that you have got a substrate. Can we take another type of substrate or have a functional substrate? And normally you select those material superalloys which are used at high temperature, which can resist to creep and oxidation. And then you can have a bond layer, thermal barrier layer, And this is to enhance mechanical bonding between the underlying substrate and the top layer. It can have a low thermal conductivity, low thermal expansion coefficient, and so on. Then you can have another layer, which is thermal insulating, which this end and this end should have good adhesion properties. So that is going into the package of coating. Then you have got a substrate package. And then on top of that, you have got an environment. So environment can be various. So I've listed them here. It can be steam, solar, or molten salt. So it depends what type of electrolyzer you're after. So it will have impact on it. So just there may be abrasion if you're having molten salt passing through the surface. Over the surface, erosion, corrosion, contamination, material will be retained on the surface, and because of mechanical load, things will degrade and also aging. So all these combination will be there when your electrolyzer is in operation. So you have to think about a layer on top. I've called it functional multiple layers, and you can have certain properties, so that you can have a longevity or sustainable surface. So it can be a sacrificial layer with low porosity and resistance against molten salt, the good thermal stability, high hardness, low wear, means it should be wear resistant, and no oxidation or change in color, better thermophysical properties, and so on. So there's so many in the list. So selection of material for the top is not easy. But there are literature which can help us to come up with a better material, which otherwise have not been considered yet for these electrolyzer application. And then once you have deposited it and you are using it for those electrolyzers, measurement, in situ measurement I'm referring to, in situ measurement is not an easy task, because we would like to know the abrasion happening, erosion happening, the corrosion rates. In all these cases, the material loss is happening, or material is being deposited layer by layer, or contamination, thermal, mechanical degradation happening. So as if you increase all these, the duration, as I mentioned earlier, hours and days and weeks and months, so you can have a sustainable design of the system. So we have to look into the details of these layers when we are manufacturing it. Right, looking into the materials processing and the manufacturing. So these material fall into the category of critical raw material, or CRM. And if you're thinking about electrolyzers, there are a number of elements which are critical, and it is only a finite source. We don't have infinite source, and also access of these material from various countries. So actually you do mining and you need to mine in a way which can be used for these electrolyzers. So over time, we expect the demand will go up. So we need to have some system on it. Now, if you break it down across material types and also countries, you can see there are a number of countries who have got those critical raw materials. And I'm just taking example here, those material which will be needed if you're thermal spraying the components. Now, these material access is not easy because these are, you have to process it, you have to mine it, you have to make it pure enough, and then send across to different part of the world to manufacture it. So there are issues which is going to be a challenge in time to come if we are talking about a hydrogen economy worldwide. Right. So one of the things which I have worked earlier as well is manufacturing electrode. So this is uh, a snap of thermal spraying in a chamber where we are using air plasma spray. And you can see you just put a different substrate and you can spray continuously. You can have a control on the process parameter. So it is like a chamber, coating chamber, both of sides of a small room. And then you have got all control panel outside, then you control the process parameters so that you can have certain thickness, porosities, and you can change the flow rate. And so there's a number of parameters you can change to control the microstructure you want to develop for various applications. So this is an example where we develop anode coating on high temperature low electrolyte substrate. So what happens, the particle is being sprayed through the gun. This is a robotic arm, and you do the sandblasting of the substrate. So this is a cut. And then when you spray, the powder particle will fill in all the surface and develop layer by layer. This is a typical fractured surface of the coating flake. What we did a deposition of alumina, which is very brittle material, using air plasma technique, and took the flakes off the substrate and then broke the flakes in a cryogenic condition. So we just wanted to see how the cross section looks like. It is not polysurface, it is a fractured surface. So we were able to see various features in it, and those features is, you can see, this is the typical splat, how it looks like. There are gaps, there are porosities, there are few micro cracks here and there, like these ones. So this is what you expect. There may be some in another snapshot. There were a few particles which were not completely melted. It was just sitting in somewhere. So these are, it comes with a range of advantage and disadvantage. So this is how the microstructure could look like. Now looking into the modeling, characterization, testing and qualification. Now, from my investigation, looking into the literature, high temperature modeling is poorly or little investigated. So there is a scope to develop modeling in this area, either solid oxide electrolysis, steam, or high temperature, or if you want to do thermochemical. So those who are interested in modeling, you need to look into a range of things as an input parameter, and you can analyze like geometry, materials, electrochemical mass transfer, thermal balance, and each of those you have to look into. So these need to be carefully looked into so that you can have a desirable outcome. And there are a number of input parameters you have to select, quite a lot. Again, selection of these, how do you select is a big question. What dimension, what size, if you're designing a channel, why certain design. So the quite a number of things you have to be careful when starting the modeling work. Eventually, you would like to design, understand the system using theoretical means, computational means, so that you can use those in your manufacturing later on and testing. So this is something, an area which, in my understanding, it requires a lot of investigation, especially at high temperature electrolysis process. Now, there are a few examples. You'd like to do the testing on those electrodes or coatings. So you'd like to know how strong they are. So this is one of the methods where what we did, you have got a substrate, and then you develop the coating on one side, two different materials. So that is how the disc looks like. And we put a strain gauge and compress. So we call it a diametral compression. Normally, you use diametral compression on rock samples, on a quartz sample compresses to find out the geomechanical behavior of those core samples. However, in this case, we took a small slice, like a disc shape. On one side, we did the coating using plasma spray and put the strain gauge on either side. So these are the strain gauge on either side, and you compress it. You compress it on a huge machine, and then try to see the strain as you compress. So then we did a neutron diffraction measurement on this coating and compared the strain at which point the coating will come off or start failing. So we were able to see those features, and we were able to relate. This is a destructive test. So I was able to relate with a non-destructive neutron method because all these component electrodes, when you manufacture it, it will go through various loading scenarios, twisting, bending, high temperature, thermomix, all these things happen. So we need to understand how strong they are. This is an example where same material we put in front of a neutron beam. And what we did, we selected a few points in the coating. One point at the interface or as close to the interface, and few point in the substrate. So this is the electrolysis substrate. This is a coating about 300 micron thickness, just over 250, I believe. Yes, and then each point measurement you do, neutron scanning. So each point takes about 4 hours. More time you spend at the interface, and then half an hour each in the substrate. So what happens, you actually measure the de-spacing in the lattice and use a formula to find the strain build up through thickness. Assume you have got a very high tensile stress in the surface region and very high compressive. So you would not want to have a huge gradient through thickness and huge gradient at the interface. So these will be not good enough if you're applying any external load. So it will fall, it will delaminate, or all sort of degradation will happen. So you can use this method to find out how even you can put this coating at high temperature and do the testing non-destructively. So this is how the profile looks like. You can see the strain is largely tensile. And it goes near to zero, the interface, but the interface for substrate very high compressive stress, and then it goes tensile. So that is how the coating substrate system looks like strain wise. Now, this is means we did many other investigation on this. The idea is we need to know how the strain value looks like so that you can use for further application. Now, thinking about mechanical load, if you are just doing simple contact on a surface, here we are using Vickers indentation, and the load, we varied the load, so 25 kilogram force or 400 kilogram force. So what happens when you apply load, it lands on the surface. It is a very semi-static process, but it degrades the region, the material significantly. You can see the huge material crack has happened normally at the edge, and that the densification happened because these these coatings are porous. Now, when you remove the load, when you remove the indentation, there will be relaxation in the stress. So when you remove it, the relaxation can induce lateral cracks, and you can see all these cracks. So actually the indentation was very localized. The size was about 50 micron, but this went on for a very long length. And you may feel from the surface, oh, it is only local fracture happening, like local fracture happening like this, but after removal, it has penetrated deep and laterally. So you may find crack appearing very far off. So any little contact or debris going in static and dynamic condition, it will degrade the surface significantly. And if you do it over a period of time, then that is how the coating will degrade. So this can be your catalyst layer, electrode layer. So again, the thickness, the porosity, all these things will influence, means the process parameter you select to manufacture those is important. So most of the people who work in this area, they try to optimize the process parameter for enhanced behavior. Now, for here, what we did, we selected different material, different way of manufacturing it, and using the same load to do the Vickers indentation. You can see the fracture is very different. So it depends on the material on which you are indenting. It can be having a crack. It can have just a chipping at the edge with no crack. It will have a very unconventional, a very different type of indentation impression on the surface. So it depends significantly on the material type. And if you've got a composite material like tungsten with cobalt and so on, so again, things are, so this is a good example where we compared that the same probe, different material, different fracture will happen. So in this case, you can see there's no cracks. So this is the desirable one, that crack stays localized. But here you can see the crack has gone very far off from the impression. So that is undesirable. But again, if you do the cross section, when you do the cross section of the indent, you can see subsurface, the lateral crack has gone very far off, even though on the surface it is very localized. Now, if you'd like to know more about various tribo mechanical responses of various type of material and also corrosion, you can look all this literature. We have looked into sliding wear, scratch, corrosion of these coatings. So combination of all these is necessary if you're developing electrode material for electrolyzers. Now, life cycle assessment is very important if you're talking about hydrogen economy. So this is a typical cycle starting from raw material extraction, material processing, manufacturing, remanufacturing. Remanufacturing it will be new or can be new in electrolyzer domain. Assembly, product use and reuse, because all these electrodes, they are made of expensive material. Can we use it, reuse it for some other application, which we don't know yet about? So, and then again, what you do once it has ended. So that is something we have to be careful. We have to look into, if we are doing any research, we need to look into life cycle of anything we do actually, to have a sustainable planet. Right, we are next few slides. Now, selection of material, a reliable material and sustainable material is very important. We need to think about using abundant feedstock material. Means we have got access to water, sunlight, heat, and electricity. How we use it efficiently. So it comes down to the selection of material. And then how we are deciding about those. So we need to look into some mechanism. If we have got so much data, we need to use various data analytics approach to come to a decision. And also how we can have an optimal design of various parts or components in electrolyzer, reducing the cell mass. We would like to have a reduced cost of those. How we do that? There are many advanced way of doing it. Enhancing the working life, more efficiency. One of the area which I'll be interested in is structural health monitoring of high temperature electrolyzers. Is very little work which has been done in the area. A lot of work has been done in fuel cell, unfortunately not in electrolyzers, in any electrolyzer types, not even in PEM. So that is an area which requires a lot of investigation. And also, last but not least, is the ethical issues, legal issues, geopolitical access to those material, uniform development of hydrogen economy globally, and so on. So there are a number of things we have to look into. And this is a simple schematic diagram, how we can use the big data and data analytics approach, because whatever you do, there is data. You may also find that a lot of data not available. How we generate that data? So you take data from literature, those data which is missing and not available, either you do experiment or do simulation. So combine all these, then that you can use that data to understand a number of things in electrolyzer business. So this is an area which I believe an area of growth, because we are dealing with a lot of materials, a lot of manufacturing method. So either we do firefighting, select one material and try to enhance the efficiency, or try to do a better way, a smarter way. Right. Now, last 3-4 slides, which is my ongoing work, our ongoing work. So recently, we have started working on, in collaboration with University of Surrey and supported by NNL and ENGINE-X, we'll be working on thermally sprayed catalyst, where we'll be manufacturing meta material or meta surface for high temperature application, where steam will be used. So watch out further output from this work. And then we recently finished a project with NNL where we looked into feasibility of using coatings for modular thermochemical cycles, high temperature, of course. And then very recently, we have been funded a Beam Time, where we'll be looking into a strain. I mentioned earlier that if you've got assume this is your substrate, which is like a flat surface. If you do the coating on it, the strain buildup will be different. Now, if you have got a substrate where you have got like a grooved surface like this, and then you do the coating. So this is an example which was not intentionally grooved. It was having just a simple scratch, because this depth is very tiny, about 10 micron or less. So when you do a spraying on top, you can see the powder particles or sprayed particles goes into those groove region. Actually, the strain will be very different when compared with the flat surface. So we need to prove the hypothesis how the strain will looks like. So what we are offering is if I assume my hypothesis that we should not be spraying on a flat surface or do any coating on a flat surface, we have to have a grooved surface so that you can have an increased fatigue life of the coating. And this will be very useful for any electrode or catalyst manufacturing. Right. So from my understanding and opinion, I see there a huge opportunity to work in high temperature electrolysis. And this is something I look forward to work on with my colleagues, collaborator, partners, and also any new interest if anybody you have got. Thank you. Thank you very much.
Okay. Yeah, thanks very much, Faisal. That's a fantastic presentation and a very good coverage of the electrolysis process and other coating enhancing process that have been involved in manufacturing of the electrolysis electrolyzers as well. So I think we got a few questions, so we just ran through them. So we got down the chat. We got one from I think it's just starting at the top. So you got one here. This is a question by Vish. Is better hydrogen generation expected? High throughput with thermochemical than steam?
Right. Means a comparison has not been done, because thermochemical electrolysis is very new. There are only 3-4 countries who have invested in this technology, which is like Japan, Canada, US. So there is not such comparison which has been done about the yield. But because you have got a lot of heat wasted through that process, once you have done a lot of work which has been done, then only you will be able to compare, and you can enhance the efficiency, because the coating degrades very fast. So the cost benefit analysis has to be done, and these are not a cheap material. So I would say it is very early on. We need to do a lot of work in this area.
Okay, thank you. There's another question here by Kumar Patrigola. This is a very interesting presentation, Faisal, for the nuclear to hydrogen application. Are you saying to divert the current existing base load nuclear reactors to produce hydrogen, or build new nuclear reactor to produce hydrogen?
It can be implemented to existing nuclear reactor, but it can also be constructed for future small nuclear reactor. So it depends, how you design your electrolyzer, how you use those, extract those heat, high temperature. That is a design problem and the material manufacturing problem. Integration is easy bit that can be looked into, but we are addressing the high temperature sustainability of the material here. Thank you.
Okay, so there's another one from Mahmoud Hussein. We know that guy. Is coating of PT on porous ceramic can be made using thermospray? Can PT enter the pore inside?
No, in my understanding and knowledge of the literature, platinum has not been sprayed because either you need in wire form or in a powder form, and I have not come across. There may be a few examples, but it's not something very common.
Okay, there's another question from Lehan Ahmed. And the question is, are there any applications of thermospray in hydrogen storage?
Right, so phase change material is one of the area which has not been looked into, where thermal spray has been used to have a phase, means there are phase change material, but not using thermal spray. So that is an area of future work.
Okay, maybe as I wait for another question to come through, so I can ask one of mine. You mentioned the high temperature is actually a high energy consuming exercise, and given the so many thermal electrolyzers we need, or other chemical electrolyzers, we need huge volume of them. So do you think this process is sustainable in the first place?
It is difficult to answer is sustainable or not. I think the best we can do is to select those material from the library, which is cheaper, easy to access, easy to manufacture, and consider those one to start with. Unless you have got abundant material to manufacture those. So yeah, that is what my approach will be, to use the commonly used material or enhance the efficiency by having a meta surface or some different design of the channel which help enhancing the efficiencies.
Okay, so can I ask again along the same line, in terms of mass production, because we will need them in large quantities, is this process scalable and easy to scale up? If any of those processes at the most site?
Yeah, thermal spray method is a scalable method. It is industrial method. It is it depends what you mean by scalability. So it can be sprayed on a meter by meter area in few minutes. In 5 minutes, it can be sprayed. So it is industrial method. Large surface are being coated using this technique. Now, application in catalyst manufacturing is new. it is happening in the lab scale currently. But whatever lab scale they are doing, actually they have got an industrial facility in lab to do the deposition of this material. So whichever lab you go, it is not like a tabletop, it is actually a proper facility.
Okay, good. I think there's another question here. Do you have plans to set up a lab scale electrolysis work for H2 generation? Would be interesting collaboration in trying various thermal spray composition on electrolysis parts. That's by Vichy.
Yes, hi Vish. Yes, I know you. So yes, we'll be happy to discuss about having such resources. You already have a facility, so we can do right away. Thank you.
There's a comment and a question or by Marcelo, who was asking whether the presentation will be available, and I think the answer is yes. Okay. Can I ask another question? Maybe another one will pop up and just trigger discussion. There's obviously a huge variety of materials you mentioned out there, and most of them are difficult to get. Now, in terms of reuse and utilization, if you try to use some of those materials from recycled materials, is the quality likely to be very poor, given that you're using thermal process in the first place?
Yeah, that's a very good question. Now, in thermal spray, reuse is not a commonly used word, because once you do the coating, removal of coating is quite a process, because it is manufactured at very high strain rate. So it adheres very strongly. So removal, there is a process, water jet process or laser method. These can be used to remove it. But once you remove it, because it will come off in the shape of flakes, little bit, or powder form. So then you have to collect all those and then reuse it, reprocess it. So there is an opportunity, but very few work may have been done. I understand. I've not done any search in this area, but it is possible to reuse those material, because there are techniques developed which will help you to remove the coating. Few years ago, it was not possible to take the coating off unless you apply hammer and smash the surface.
Okay. So it looks like there's a lot of.
Sorry, I miss your voice. No, can't hear you. William, if you can hear me, I see your question here. Is any investigation being done into use more abundant material rather than more rare ones? Yes, means there are a number of material in the list I have shared. They are abundant because people tend to use those material which is easily available. But there are some other indications that alternative material can also be used because they tend to be better. And as soon as somebody proves it's better, then suddenly you feel is not enough material available. So yes, it is people are looking into.
Okay. Can you still hear me, Faisal, now?
Yeah, I'm okay now. I can hear you.
All right. Okay. So for some reasons, I was kicked out for a little while. Okay. So I don't know if you got more questions out there. Faisal, I wonder if you can comment. You showed a very interesting picture in terms of billions of miles that we travel and the amount of hydrogen that we need, and that's a good thing. But what happened to the oxygen that we get from there? If you're looking for, instance, like blue hydrogen, green hydrogen, there's a lot of carbon dioxide produced. There's a lot of oxygen produced. Could you comment around the future of these hydrogen and carbon in terms of our lives and our lifestyles in the future? Because there's a lot of a lot of hydrogen and carbon dioxide we're going to produce through that process of producing hydrogen?
Yeah, anything beyond normal is not desirable for human being. So if you have got pure oxygen, the doctors can tell you better what happens to our lungs. So there is always some risk with that. What happens, very difficult to say, but I believe one thing I know that we don't want to have a lot of hydrogen leakage happening into the atmosphere. Assume you are storing in a storage. If there's a lot of leakage, then it will, because there is a natural process of the environment which cleans the environment. So if hydrogen percentage goes up, so that cleaning process will be reduced, and that will impact the environment. So that is something we don't want to go in that route. So leakage is another area of hydrogen. So how it will impact hydrogen, again, pure hydrogen is useful, but for human being, you need a mix of those, to inhale. So I've not done any investigation yet, but I understand anything you do beyond norm, then it becomes a problem. Thank you.
There's a comment or question by Mamdood Hussein, but I guess you can store and use oxygen, but what would be H2O condensation? If I guess that right, the implication is that you can store hydrogen, or sorry, you can store oxygen and try to utilize. But if you're producing 16 billion tons?
Yeah, 16 million kilogram per day. That is that will be needed. Yeah.
Yeah. So there's a few billions of it, or millions of. Then there'll be tons and tons of these hydrogen, sorry, oxygen lying out. So should you be converting to water? I don't know. Mamdood, we may need a simulation there to see what the scenario, what if scenarios look like. Yeah, and maybe on a further comment on there is also to look at the soil sinks, because the soil cannot absorb as much hydrogen in the atmosphere. So fine, so can I bring you back to manufacturing world again? The hydrogen production obviously is an interesting area. The factories will come up in a short while. What do you see that impacting cost in terms of quantity? I mean, we're sitting still at reasonable price, but still high. $6 per kilo. So.
Are you referring to thermal spray method or any method?
Yeah, in terms of impacting the cost to go down, perhaps.
There are a number of elements. If you think about manufacturing cost, the basic is the material, the raw material, and then the processing of that. So initially, when you are at R&D stage, things, especially in thermal spray, it is expensive. But once you have established, optimized the material and the composition, and also the structure and porosity and many other features, then you can have a scalable production, larger scale. And because you spray at very high strain rate, so the coating quality is better off than the other method. So you have to do a lot of cost benefit analysis to fine tune. It is expensive initially. It is not cheap technology. But once you have established it, then it could become cheaper. If you consider other aspect of the issues, like other manufacturing technique doesn't sustain high temperature in, say, thermochemical. Because they are not able to handle that temperature and corrosive environment. So you need, and you cannot use just a base superalloy because that doesn't work. So you need to have somewhere in between a coating, and it is a costly affair. Either you use the high temperature to produce some hydrogen, or you do nothing at all. So that is a judgment based on the cost benefit analysis will be needed.
I'll probably ask one more around manufacturing then. Is it easier then, do you think, for manufacturing businesses which are focusing on high temperature on other products to shift to hydrogen manufacturing businesses, or sorry, hydrogen component manufacturing businesses?
It is easier to come to this business and develop hydrogen electrolyzers, which has been thermally sprayed, because we drive automobile every day. So all the liners, cylinders, they are coated by thermal spray. All the turbine blades of aeroplane, they are coated by thermal spray technique. Pipelines, where you want to reduce the corrosion of pipelines in offshore condition or chemical processing application, they are coated by thermal spray. So it's a very big application. So the sector can easily adapt and start developing electrodes using thermal spray. Yes.
Okay. I think we don't have more questions, so I'll ask the last one. What's your, how do you see the future look like from your perspective, from hydrogen world and manufacturing linking?
Okay, right. So I see that it is an ambitious plan by the government. There is an opportunity. Whatever happening is happening like in an island. Everybody's working, everybody's planning to do things. But when I look back and see the issue is massive. There are a range of materials, manufacturing methods, and every of those produce a lot of data. We don't know what we want to do, and then we try to optimize those. These are the problem. Yes. Now industry is more interested in using those methods, which is proven high technology readiness level. It is a risky to go for them to go in another manufacturing methods. So we have to bridge that gap. We need to, academics need to connect with companies and develop technology for high temperature application as well. And we do in a more scientific, comprehensive way, and not do firefighting in designing those. It takes time. It may take 10 years, I believe, if there's a lot investment happening in this area. It cannot be done in 1 or 2 research groups or labs. It requires a joint effort to solve the problem, because somebody may be great in modeling, somebody great in manufacturing, somebody just understanding the bigger picture. So we need to come together to solve this problem if we want to achieve that target by 2030. Otherwise, what I see, we will still have 1 or 2 technology going ahead, the rest of the thing left behind, because they will say, oh, it is not sustainable or not economic to do it. But if you have to cater these needs, you need to have a usage of all various technologies to cover for the requirement. Yeah, thank you.
First, I was about to let you off, and then there's a good question that came through. Do you want to answer this, and then we can probably close to that?
Can you read that? In my screen, it shows very big text.
What is the relative energy efficiency of hydrogen power? That is energy that goes into production versus energy produced from hydrogen. There are specific requirements of electrodes for mobile transport, hydrogen applications, compared to stationary applications. I think there's 2 questions.
Yeah, so in terms of what is the relative energy efficiency of hydrogen power, that is the energy that goes into the production versus the energy produced from hydrogen. I have not done that analysis myself, because I'm materials manufacturing. That calculation, I can do it for you very easily. But what I understand is the energy, the efficiency of some of these electrolyzers like PEM, about 55–60%. The main thing is currently, because of renewable energy, wind turbine, a lot of nuclear power plant, a lot of electricity is available that can be used for these electrolyzers. Either you use it for electrolyzers or don't use it. So as soon as you start using it, you see the is better off than not using it. Now these heat are wasted. Can we use it? So suddenly you see the value. Now, again, analysis has to be done, but I don't have any number for now.
Okay.
And what was the next question?
I think on the same question, you mean?
Yeah, are there specific requirement for electrode for mobile?
Yeah.
Transport hydrogen application? Right, so for transport, you mean you want to produce hydrogen during transportation? The question is not so clear to me. Oh, maybe you want to use hydrogen for transportation purpose. So it is like in Aberdeen, we have a bus where hydrogen is used. So you fill the hydrogen tank in a pressure vessel and use that hydrogen into fuel cell, and fuel cell will power up your automobile. So that is how you use. So you need to store hydrogen in a secure container. That is the basic requirement, and it has to be lightweight, so that, you know, for various reasons, it has to be strong enough, it doesn't breaks down. So these are mechanical engineering requirement.
Okay. Alexander, do you want to ask the last question? And very last question.
Yeah, thank you so much. Can you hear me?
Yeah.
Yeah, we can.
All right. I just wanted to ask. I wanted to bring it back to the recycling and reuse of the material, because I think that's one of the major conversations when you're talking about net zero. That's the fact that um, you can materials can be easily utilized, possibly reused or recycled. So I just wanted to gain more clarification for the materials that are going to be used. These materials that are going to be sourced that quite expensive. Um, what are the opportunities for recycling them and reusing them? You did speak about laser briefly, but just wanted to just to be simple, can these materials be recycled, reused for another purpose at the end of the day?
Yeah, so recycling industry need to come up because just take simple example. You use washing machine or dishwasher. When you want to throw it, the manufacturer of that dishwasher, they don't want to take the dishwasher back. Similarly with microwave, and similar with other appliances. So somebody have to come up and use the material to recycle it, repurpose it. Similarly, it has been done in other areas, because I believe it can be recycled. Even if we can have 10% output from that recycling process, is still useful than just using as a landfill. So I definitely think that will be a good thing to do. And I don't think that the manufacturer of those electrolyzers, as usual, like other business, would want to claim it back, unfortunately.
Okay. Well, thanks very much, Faisal. I think we appreciate all the time we got and for all the questions you answered, and a very good presentation. Very nice speaker to have, and of course, very nice audience. Thanks everyone for participating, and a lot of good questions there. And most of all, also thanks Gemma for organizing the day and the webinar, and also the folks from NSC for supporting us with the launch of the event today and the future ones. So Faisal, thanks. Have a nice weekend, everyone. I'm James Juguna, and bye-bye for now.
Thank you. Bye.